But so now,
now they're visible.
now
Looks
they're
good.
visible. No, okay.
Yes.
But, yes, thank you. I'm delighted and honored to give a talk in the first Congress and in honor of Louis's anniversary. Let me say that I'm very saddened to hear that Roger Fenn has passed away very recently. And in fact, my first work in knot theory was inspired by his paper on doodles, and I sort of found some analog of the braids whose closures, which consist of elements whose closures are doodles, and I wrote about this and related matters. That was back in the late 1980s, early 90s in the Soviet Union, which was about to become Russia. And back then there weren't many computers available, so someone helped me type it, and I sent it to several people in the West, including Louis, and I was thrilled maybe a year or so later to find out that he included a reference to my preprint in his book Notes in Physics. So that was great. And let me kind of just tell you a little bit about my graduate years, which were back in the 90s. So I was a student at Yale, and I ended up working with Igor Frankl. Igor is a renowned mathematical physicist and representation theorist. And so what he was doing was very hard for me on the algebraic side. So eventually I settled on working with SL2 and quantum group SL2, which that had not huge amount of algebra, but of course immediate connections to topology. And at the same time, so I was studying representations of quantum SL2 and their connections to topology. I was reading Louis Kaufmann's books, including on knots. That was my sort of table book, Knots in Physics, Formal Knot Theory, and his book with Sosthenes Lins, Temporal and Libri Coupling Theory and Invariance of Three Manifolds. And that was, of course, everything in this book is about representations of quantum SL2 at generic U and roots of unity. So that was kind of very close to the things I was working on with my advisor, Igor Frankl. And they were really very inspirational books in many ways. And also during my graduate school years, Louis invited me to visit him. I went to Chicago. So it was a wonderful visit. He showed me various things he was doing with his students, including, for instance, looking at four-dimensional fractals, where you replace complex numbers by quaternions, and then you look at level shapes of these fractals, and you see something like a starship as a shape set was extremely interesting and inspiring. And so I was definitely very heavy on reading Louis's books. And also at the same time, we were looking at Frenkel and Crane's idea that so what he saw at the time and Crane saw at the time was that so on one hand, we had this explosive, remarkable developments in quantum topology with quantum invariance of links, starting with the Jones polynomial that appeared and their connection to quantum groups. But at the same time, there was, and I think that was important to realize, at the same time, there was the geometric representation theory, where, for instance, so let me scroll to the next slide. In the geometric representation theory, various familiar structures in representations of the algebras, representations of symmetric group, Hecke algebras, and quantum groups, they live to categories in the sense that you recover. So let me just go a little bit slower. So you can start with this dual pair in the upper left corner. This is where you have a vector space V of dimension K. Vector space V of dimension K, and you take its nth tensor power. And then you have the symmetric group acting on the tensor power by permuting the variables, by permuting terms of V. And you have a commuting action of the group GLV, so vector space V, you can replace it, you can linearize it to the action of the V algebra GLV, which is of course the same as the action of its universal enveloping algebra. So you have these two commuting actions, and then you can check that each action is the commutant of the other, so that everything that commutes with the action of GLV comes from a linear combination of elements in Sn. And vice versa. So this is an example of a dual pair, and this is known as in this case, as the Schur-Weil duality for representations of Sn and GLV. And after the discovery of quantum groups, people immediately realized that this can be Q-deformed or quantized, where representation V is now a representation of quantum SLK. The commuting action is that of the Hecke algebra, which is a deformation of the group algebra of the symmetric group. And I think this is a primary structure for representations of quantum groups, representation of quantum SLK. So at the same time, people were studying sheaves on various varieties, including flag variety and partial flag variety. And the motivation was the work of Każdy and Lustig, who found the basis in the remarkable basis in the Hecke algebra by studying sheaves, by realizing this Hecke algebra through convolution of sheaves on the flag variety. And this gives you a basis of so-called simple perverse sheaves, so simple objects in a certain abelian structure on that category. That was back around 1979. And after the discovery of quantum groups, Lustig found a similar geometrical interpretation of the universal enveloping algebra, and more precisely of its positive half, using sheaves on suitable modular spaces of quivers, of quiver representations. And also people, this is the work of Benson, Lustig, McPherson in 1991, they interpreted the action of quantum SLK on the quantum SLK on the nth tensor power of V by looking at correspondences between partial flag varieties, where the index K, the dimension of V, becomes the number of intermediate subspaces you put between 0 and your n-dimensional vector space over Fq, a finite field where n is the number of terms in the tensor product. So somehow, for instance, if you have just SL2, if K is 2, you can just put one intermediate space. L2 then is the whole thing. So put one space, and then you can set up correspondences where your subspace goes up or down one dimension. And when you count the number of points to see what happens on the flag variety, you discover that you recover structure constants of quantum group, quantum SLK, with EI moving the I've subspace one dimension one step up, and Fi moving that subspace one step down. And so that was also a geometrical interpretation of the quantum group. I mean, so based on this, Igor Frankel conjectured that we should really not just look at special bases, because back then somehow the attraction was that we get this new basis with remarkable positivity and integrality properties. And so Frankel proposed to study the entire category and study functors on these categories. And so shortly after I graduated from Yale, we wrote a paper on this in the case 1, case 2. And in some sense, we just repeated what people already knew in geometric representation theory and representation theory in the study of so-called highest weight categories of representations of SLN, where n is this index, the number of terms. We sort of more repeated it in a simpler language, without sheaves, just talking about blocks of category O. So just briefly, category O is it's also called the highest weight category. It's sort of a model category. It consists of certain representations of the algebra SLN. These representations, most of the time, they're infinite dimensional, but yet they have finite length. So they build out of finitely many, usually infinite dimensional representations. A typical example would be take a Verma module over for SLN. So take a highest weight and everything below it. And that's an object of category O. And it also has a unique simple quotient. And that simple is usually infinite dimensional. And that's an example of what category O is about. But in category O, there were many so-called translation functors. And translation functors, they what you do, you take the functor of tensor product with a finite dimensional representation. So your category consists mostly of infinite dimensional representations, but you take finite dimensional representation and tensor with it. And then the category from the start breaks into many pieces according to the values of the center of the universal developing algebra. And then you do this translation functor, tensoring with a finite dimensional representation. It has many summands because you can project it into various pieces, various blocks of category O. And in this way, you get many functors. And so Igor observed that for suitable block, for suitable functors, you can actually get the action of E and F on the Grothendieck group. The Grothendieck group can be identified with V tensor N, where V is the two-dimensional representation of SL2, of the algebra SL2. I mean, everything is very combinatorial, very explicit, and it's not hard to compute the action of these functors on the Grothendieck group in the basis of Verma modules. And then you just see the action of generators E and F of SL2. At first, there is no Q, there is just SL2. And so we wrote about this and about the commuting action of the Yankee algebra, which when case 2, this factors down to the temporary algebra. So for when case 2, on one hand, you have E and F as functors, as translation functors, but you also have the action of a temporary algebra by so-called Zuckerman or Bernstein functors, which are derived functors. But we check the relations in them to get the temporary algebra. And you can also flip everything. You can pass to so-called causal dual situation, going from singular to parabolic blocks and that. And this flips the actions so that SL2 acts now not by translation by Zuckerman-Bernstein functors and vice versa. So there are two cases. And so this was sort of going from kind of geometry and to saying we want to study these functors and their compositions. And there's been lots and lots of work since then. Let me first go back to the more diagrammatic approach and recall the celebrated relations for the Jones polynomial, the skein relation. And as we all know, Lewis found one canonical way to think about the Jones polynomial by simplifying and saying we just need this relation. And one way to think why this relation works is that we're going from 2 copies of V, representation of quantum SL2, to 2 copies of V, and the space of Holmes is 2-dimensional. So there has to be a relation on these 3 intertwiners of the quantum SL2 representations, but with the caveat that we are explicitly identifying representation V and its dual by not orienting the strand. We are implicitly identifying representation V with its dual, which is possible specifically in the SL2 and quantum SL2 case. So we have the skein relation. This is what we need for the circle. This is the additional relation that we have. And so then sort of if you start thinking, if you go back to this setup and start saying, well, we have the temporary algebra acting by functors, SL2 acting by functors. So This is now a category. So there should be, so this should be now functors. And it's okay to have derived functors. You're quickly forced into, from exact into complexes of exact functors into derived functors here. So you need derived functors. You could say, well, maybe you can have, so this is a functor, this is a functor. Let's take a cone, let's take a morphism between these functors, a natural transformation, and take the cone to try to get the crossing. And in some sense, this was already there in the geometric representation theory. People just kind of were not investigating this particular extra structure. So this was present in the Zogid category, which categorifies the Hecke algebra, such break group action. But you can just try to avoid all the difficult categorical story and just do things by hands. And if you do this, you'll see that you can lift everything to the next level by replacing Q plus Q inverse by a two-dimensional Frobenius algebra over some ground ring R. This Q plus Q inverse becomes, for instance, cohomology of the two-sphere or CP1 up to an overall shift. So you can just build things up. You just need using because you want to have a map from this object to this object, and this map should be given by a saddle point, saddle cobordism, and then it's enough to have a Frobenius algebra structure on the circle, because that gives everything. That gives cup and cap and a saddle point for cobordisms between unions of circles. So you build inductively. We can build a complex for diagram as a cone of iterating the cone construction for these complexes for diagrams with one less crossing, and the Q becomes the grading shift. So in some sense, it becomes a very simple thing, just extra grading. But this extra grading is often hard to see categorically. So it's hard to see in highest weight categories if you use the standard definition as category O, but it's easier to see using shifts. But so it becomes the grading shift. And so I want to point out that Lewis's Skene relation, three-term relation, becomes a long exact sequence for homology groups of these three links. There are some grading shifts. And maybe I just want to kind of ask for more such examples so we can, I'm sure that there are some three-term relations known in combinatorics, in other parts of mathematics that are manifestly integral, that are on integer valued, but that have not been yet categorified, and so maybe they should be. So this is just an encouragement to perhaps graduate students in the audience to take a book in combinatorics and see if there are some three-term relations or something there that can be lifted to the next level, to the numbers to vector spaces or homology groups, etc. Just an open problem or an exercise. And I want to point out that while this is the lift of the Kaufman's relation, the original Jones relation can be categorified using this diagram, where we introduce an additional diagram here, not present in the Jones relation, where we this sort of point where orientation is reversed. And again, it's possible because of an isomorphism between representation V and its dual of quantum SL2. But if you write down the Skene relations for these two triangles and cancel out the middle term, you get the Jones relation, and there are additional grading shifts here. So eventually it was shown that this homology field is functorial for link cobordisms in R3. This is Magnus Jacobson, Barnatan, myself, and Morrison, Walker, and Clark, and Christian Blanchet using forms, and maybe more recently Taketa Sana using additional parameters. Again, I'm skipping over giant parts of the story. But let me just mention one recent application. So this started with the paper of Scott, Kevin, and Paul from 2019, saying that this homology, which clarifies the Jones polynomial, can be used as a black box, to build something for manifolds. Black box in the following sense: so take a four manifold, take a surface in this four manifold, but you allow the surface to have singularities. And I drew a picture here. So we here have a knot or a link L. This is the four ball. The boundary is S3, and on the boundary of S3 you have this link L, and sort of draw a cone over L as a singular surface in the four ball, the singularity, and take an element in the homology of L and sort of just write it here as a label. So we have a surface in a four manifold with singularities which carry elements of the homology, and then they write a skein relation, some compatibility. So suppose you have, let's say you have two such balls with two cones, one cone, another cone, with two elements of H, and suppose those balls sit inside a bigger ball. Then you can just sort of combine everything and compute the resulting element of the homology of a link on the boundary of the big ball using functoriality, where you need some more functoriality, because usually we prove it for links in R3 across the interval, but we upgraded this functoriality to links in S3 across the interval, and there were many other things to do. But they gave them some kind of skein lasagna modules of the four manifold. This four manifold may have boundary, and on the boundary you have a link, and then you're looking at everything that this link can bound with the singularities modular skein relations that come from the four ball. And they also have the derived version of the story, which is much harder to compute. And then so this there were kind of important follow-up papers, and let me mention in particular paper of Chiuren and Mike Willis last year, and they show that lasagna skein modules can distinguish exotic four manifolds. So they found two manifolds, two four manifolds with boundary, and these four manifolds are homeomorphic but not diffeomorphic. And so the way they show that they're not diffeomorphic is by just showing that skein lasagna modules, it's trivial for one of these manifolds in one by degree, and it's non-trivial for the other manifold. So that's a remarkable result based on all this on all this theory. And my understanding was before you needed analysis to prove this, such as the Donaldson-Floyer theory or Haggard-Floyer theory, or something which requires analysis. So my understanding, this is the first combinatorial / algebraic approach to exotic four manifolds, but using this technology that took many years to develop. So let me, of course, say that nowadays we have a wealth of homology theories. Let me mention that if you look beyond invariants coming from SL2, so Jones polynomial corresponds to representations of quantum SL2 and its fundamental representation. We have colored Jones for any representations. We have Homfley PT polynomial, which combines the invariants for the fundamental representation of SLN for all n. And in general, we have Reshetikhin-Torayev quantum link invariants for any simple algebra G, or sometimes superalgebra, and coloring of components by irreducible representations of G. And some time ago, maybe about 10 years ago, Ben Webster, he came up with a clarification of all such invariants using many ideas. So he had to clarify tensor products of representations of quantum groups. Before that, there were kind of verifications of just quantum groups by themselves, so that also took time to develop. And let me, so in some cases, in special cases, use homology coincides with earlier homologies. There is still an interesting open problem. In general, Benz homology and many other homology theories that we know, they cannot be functorial for link cobordisms for various simple reasons. For instance, because, because if you look at homology of the unknot, homology of the unknot is not finite dimensional over homology of the empty link. So because to have functoriality, you would want homology of the unknot to be a Frobenius algebra over homology of the empty link. So you can do the simplest possible cobordisms, giving you a two-dimensional TQFT. And for many theories, we know this is not the case. So that's a general open problem for us. How to extend various link homology to link cobordisms. But what we do know, we have a sort of gold standard which works for SLN homology, and when every component is colored by some exterior power of the fundamental representation V of SLN or quantum SLN, so V is Cn. So for these homology theories, and this has been work of many people, for these homology theories, we have functoriality. And this homology theories, well, when K is 1, this homology categorifies the Hopf-Lipiti polynomial at q to the nq, at parameters q to the nq, with this skein relation, which is modifications of a Jones relation, where we replace q by n. This is the value of the unknot. And just to remind you how this works is we, well, of course, this is enough to define the polynomial and compute it. If we want to categorify it, we use the Murakami-Atsuki-Yamada graph model, where we replace the crossings by linear combinations of these diagrams, where now we need these graphs. This is sort of a double edge on a graph. And after you expand every crossing, you get a linear combinations of such planar graphs. And extremely convenient thing for us is that this planar graph, and you can think of this graph as these graphs are just the intertwiners between tensor products of representations of quantum SLN. So this, for instance, this piece is an intertwiner from the tensor product V tensor V to the representation here, which is sort of deformation of the second exterior power of V, and so on. So all these pictures are that of intertwiners and their compositions. And then you take the whole composition, you go from a trivial representation to trivial. So this becomes a number. And it's quantum invariant, it's a number, but it's a very convenient number. For instance, in this example, and in general, for planar graph, it takes values in Z plus QQ inverse. So it has positivity and integrality. So that's a very special feature of these intertwiners between exterior tensor powers of the fundamental representation. So these intertwiners have both integrality and positivity property, and that's extremely convenient. And that fails, for instance, for SL2 and general representations. For the corresponding pictures would be quantum spin networks, and for them we don't have integrality, we don't have positivity. But here, because of this, we are able to bootstrap and build up our homology theory by first saying that for a planar graph gamma, its invariant is in here, and that should be easier to categorify than having something in Z, because having something in Z, we have both positive and negative, we might need complexes. But if you have something in Z plus, hopefully just a vector space with additional grading to, after clarification, it's a vector space with additional grading to explain powers of Q. And so this is how it works. And so let me first say that the invariant can be computed as some kind of quantum flows. You have your graph, and then in general, in this example, thickness is 1 and thickness 2, but you can look at more general Murakami-Atsuki-Yamada graphs, and they have lines of thickness A and B, which merge into a line of thickness A plus B. The quantum invariant of such a graph can be computed by counting flows where you pick subsets I1, I2 of cardinality A and B of numbers from 1 to n. These are subsets. And they should merge disjoint into a subset of cardinality A plus B. So you sort of count the subsets, and then you look at individual line and where it goes, introduce powers of Q. But this is a possible computation for P of gamma. And again, so the idea is to first do it only for graphs, lift invariant graph to homology, and then we combine this into complexes to K-graph P of L. And there are a number of approaches to this. Let me single out for this talk the work of Robert and Wagner. And so here, of course, in their work and in other approaches, you sort of encounter forms. Because you have your graph in the plane for which you want to have vector space. But then this must be functorial. So when you have a cobordism between graphs, you want to have a map between the vector spaces for this graph. So in this picture, I sort of drew one graph, another graph, and cobordism between them given by this kind of singular line where three facets meet. And you want these things because you want to, let me scroll up, because you want to calligraphy these relations, hopefully into long exact sequences. And then you need a map between state space of these two diagrams. And then it's natural to think that it comes from some geometric object, which could be a picture like this, which is part of what we call forms. Forms are very natural. And this is a seam of the form where three facets meet. In general, forms will have vertices where A and B merges into A plus B and C merge into A plus B and C. So here we draw three parallel cross sections of the form where you see it's sort of like a stratigraphy flipping from this diagram to this diagram, and this cross section contains the vertex of the form. And just quickly remind you about the Robert Wagner approach. We do this instead of counting flows, we count surfaces. So we color facets of the form by subsets of numbers from 1 to n. So for instance, along the seam, we have this facet of thickness A. So we pick a subset I1 of numbers 1 through n of cardinality A. For this facet B, for this subset I2, cardinality should be B, and they should be disjoint, so sort of kind of flow into each other. And what they do is they look at bicolored surfaces, Fij of C, where C is a coloring. So Fij of C means take all facets that contain, whose sets contain element I but not J, or J but not I. So let me give you an example. So let's say if I is in I1, J is in I2, then the union contains both I and J. So the part of Fij is going to be I but not J, J but not I, but not this. So you see that along the seam it has a surface structure. So it's just these two facets. And so you get the surfaces, and then they take the surfaces, they compute their Euler characteristics, and they insert them into the evaluation formula for closed forms. And then miraculously, everything works. You can do the universal construction. So when you have an evaluation of closed objects, there's universal construction where you can figure out what's in the middle. So what's in the middle is a vector space spanned by everything that goes into the middle from nothing, modular relations with a linear combination of these things with boundary is 0. If no matter how you cap it off and evaluate, you get 0. So this is universal construction. Just for this particular story, let me point out that after Robert Wagner's paper, immediately Michael, Eric, Daniel Timinauer, and Paul Wejcik wrote about how this can be used to, how this extends to functoriality following cobordisms for SLN homology. And with the paper of Morrison, Walker, and Wejcik on scale lasagna modules, That was one of the inputs. And then came the work of Wren and Willis. And again, this is just kind of a set of remarkable papers. And again, there's so much more work by many people that we cannot possibly mention here. But let me point out an open problem. So this is sort of the gold standard. So since this is the gold standard, from the perspective, say, of combinatorics and algebra, here we just come up with this evaluation. Everything is over integers, everything is positive. So, and we build things in stages. We first build the homology for vector spaces for planar graphs without crossings, and then put them into complexes to get homology theory. And this is sort of complementary to the other approaches, which are more categorical. In those other approaches, we can build some functors for tangles, but for that we need categories for their boundary points, and that often requires a lot of extensive work to develop the theory of these categories, be it coherent sheaves or Fukaya-Flory categories for some particular representations or representations of some particular algebras. There's some kind of trade-offs. It's neither approach is easy. So there are more categorical approaches where you often need to kind of rely on what's already known about certain categories and guess that they are relevant to link homology. And this is sort of more, this is more combinatorial. But so we don't know how to do this for SL2 and non-fundamental representation. So how to do, so for Q-spin networks, and of course, those are kind of diagrams I was studying a lot in graduate school from Lewis's and Lynn's book on temporally precoupling theory. So we get denominators and we don't have positivity. So there are various things that people have done, but we don't really know how to. I think we don't really know how to do it, say, in a functorial way for link cobordism. So I think that's an open problem. And I just want to point out that back in graduate school, one of the things that Igor Frankl was asking me to do was, he said that to categorify spin networks, you should count surfaces, just instead of counting, for instance, lines, as you do in the Penrose's formula for the 6J symbol. So Frankl wanted me to count lines, to count surfaces instead of lines, go one dimension up. So try to clarify the Johnson projector by counting surfaces instead. And I tried that, but I didn't get far. But I think in this example, this is a success story many years later, where Robert Wagner counts surfaces in some clever, very subtle way, and they succeed. So this is still maybe like a suggestion from Frankl that worked really well for the foam case, for evaluations in foam. So count surfaces, found new ways. Maybe let me put this as an idea. Find new ways to count surfaces. And yeah, this is actually going to be a short talk, and I'd like to wish Louis a happy birthday and many exciting mathematical discoveries and ideas.
Great. Good. Thank you very much for a really interesting talk. So thank you. If anybody wants to unmute, feel free to. That was great. Thank you very, very much. Okay, so we are going to open it up